Understanding how the moon has developed would really help us in understanding how the other planets in the inner part of the solar system, the rocky planets, have also developed. The purpose of the GRAIL mission is to investigate the interior structure of the moon. To achieve that, we have to measure the gravitational field of the moon.
So we're all familiar with tides on the Earth that are caused by the moon. The moon actually has similar tidal response. And when the moon changes its shape a little bit due to those tides, just like the Earth does, we can actually measure that. That affects the gravity field. As the lunar shape varies, its gravity field changes, and we're able to observe that.
We are using a very simple measurement, which is gravity. It's a little bit like taking a CAT scan of the moon, but using gravity waves instead of acoustic waves to unlock the secrets of the interior of the moon. We have two spacecraft that are in a polar orbit around the moon. One's essentially chasing each other around the moon.
There's a part of the Earth's moon, a very significant part, the far side of the moon, that does not present its face to the Earth. So we can never directly observe the spacecraft as it goes across the far side of the moon using Earth-based tracking antennas. So the solution to that was, rather than track the motion of the spacecraft as it's orbiting the moon from the Earth, track it with another spacecraft also orbiting the moon.
It's essentially the same technology as the GPS in your mobile phone. And in fact, the two orbiters together form sort of a mini GPS and receiver constellation, except using different frequencies from normal GPS.
The first thing we do actually, once the map is in our hands, is compare it with a topography map, hopefully of comparable resolution. And from there, we can look at specific features, such as mountains and basin craters, and compare the gravity and the topography. This is where it gets really interesting. You would normally think that if there's a mountain present on the planet, there's additional mass and additional gravitational signal as the spacecraft flies over it. But if it does, and there is no additional gravity signal, then something on the inside is going on that is particularly interesting. And that's what we want to know.
When I was just getting into middle school, I had to rely on my information on the moon watching the Apollo missions on television. We wanted students to have a hands-on role in exploring the moon. It's an experiment called Mooncam. We will have up to 4 cameras on each GRAIL spacecraft. Students will be able to look at the ground track of where GRAIL will be at going around the moon on a daily basis and to propose images that will be taken. It's going to go a long way towards helping students understand just how much fun science and engineering is as a career.
The moon, it's our closest celestial neighbor. And yet more than 40 years after astronauts first set foot on the lunar surface, there are still many mysteries to solve. NASA's twin Gravity Recovery and Interior Laboratory spacecraft, known collectively as GRAIL, are ready for their lunar assignment. The spacecraft will look at the moon's gravitational field to determine the structure of the lunar interior, from crust to core. Scientists hope what they learn from GRAIL's mission will advance understanding of the thermal evolution of the moon. The United Launch Alliance Delta II rocket that will launch the GRAIL spacecraft began to take shape at Cape Canaveral Air Force Station's Launch Complex 17B in April. The rocket's first stage arrived at the pad on April 7th and was lifted into place. Later in the month, the 9 solid-fueled boosters were delivered to the launch complex and attached to the rocket's first stage. Workers transported the Delta's second stage to the pad in May and hoisted it atop the first stage booster. May also marked the arrival of the Air Force C-17 cargo plane carrying the GRAIL spacecraft. The plane ferried the spacecraft from Lockheed Martin's Denver plant, where it was built, to Florida, where it would undergo its pre-launch processing. After it was unloaded at the shuttle landing facility at NASA's Kennedy Space Center, GRAIL was transported to the Astrotech Payload Processing Facility in nearby Titusville. Once inside the processing facility, the spacecraft was uncrated before technicians attached and tested the solar panels. The electrical power subsystem on each of GRAIL's twin spacecraft includes 2 solar arrays and a lithium-ion battery. Each solar array is capable of producing no less than 700 watts. Shortly after GRAIL separates from the rocket, the arrays will be deployed and remain fixed throughout the mission. The next step for the processing team was to move the spacecraft in late July to Astrotech's Hazardous Processing Facility for fueling. With the scheduled launch just a month away, the twin spacecraft were weighed before they were stacked in their launch configuration. Once attached to the spacecraft adapter ring in their side-by-side launch position, GRAIL was placed in a protective canister for transport to the launch pad. On August 18th, the spacecraft arrived at the launch pad and was lifted atop the Delta II rocket. Technicians secured the clamshell-shaped payload fairing around the spacecraft on August the 24th. The fairing, which will be jettisoned once the spacecraft is outside the Earth's atmosphere, will protect the spacecraft during its ascent into space. The rocket and spacecraft stand ready at the launch pad, set to begin the journey to further unlock the secrets of our mysterious moon.
The moon has captivated humanity's collective imagination since ancient times. Humans have studied it for hundreds of years, first with telescopes, then with robotic probes, even sending 12 American astronauts to the lunar surface. But in many ways, our nearest neighbor remains a mystery.
And so knowing what happened with the moon will help us understand what happened with the Earth, Venus, Mercury, and Mars. And so that's the reason we want to try to understand it. We're trying to understand the past formation of the planets, and so that will help us learn the future.
Clues about our own planet's history and the influence of the moon's gravity on Earth 240,000 miles away could be locked below that dusty lunar surface. The Gravity Recovery and Interior Laboratory Mission, or GRAIL, features twin spacecraft embarking on a challenging mission to map the moon's gravity.
Its sole purpose is to measure gravity of the moon, to try to help us understand how the planets were formed and how they evolved over time.
GRAIL's 2 spacecraft will fly in formation above the lunar surface to measure the variations in gravity. The mission seeks to reveal clues about our moon's thermal history and how the inner solar system's rocky planets developed. GRAIL is departing from Pad B at Cape Canaveral Air Force Station Space Launch Complex 17. Pre-launch processing and the final countdown are managed by NASA's Launch Services Program at adjacent Kennedy Space Center.
Our team especially gets excited whenever we leave Earth orbit, and going to the moon excites us and it excites the public.
The 2 spacecraft, called GRAIL A and GRAIL B, are riding into space side by side aboard a powerful Delta II heavy rocket built by United Launch Alliance. It's a rocket with an impressive reliability record.
If we just look at the Delta II rocket, which is the version of the vehicle that we fly today, NASA has a perfect launch record, 48 for 48.
The payload for NASA's most recent lunar mission, called LRO L-Cross, weighed in at 6,600 pounds and was the size of a minivan. It launched in 2009 aboard a massive Atlas V rocket. But that extra performance isn't needed for the GRAIL spacecraft, which together weigh only about 1,600 pounds. Each unit is about the size of a washing machine, designed to be compact and rugged, a perfect fit for the Delta II. Preparing 2 spacecraft adds an extra challenge to the team's workload, from environmental testing before launch all the way through the countdown.
And then, for instance, on launch day, we have 2 dedicated teams, one to GRAIL A and one to GRAIL B, and they'll have to individually power up each spacecraft and go through their health checks and put the spacecraft in the proper configuration for launch.
After the climb to orbit, the GRAIL spacecraft will be released from the launch vehicle one at a time as launch controllers and managers on the ground wait for news of spacecraft separation.
So we will definitely wait to celebrate until both spacecraft are safe and on their translunar cruise to the moon.
GRAIL's journey to the moon will take 3.5 months, a mission plan offering plenty of time for controllers to make sure the spacecraft are ready to get to work.
And regardless of when we launch, we're going to have a constant arrival date. So GRAIL A will arrive on New Year's Eve of 2011 and GRAIL B will arrive on New Year's Day of 2012.
Each spacecraft will have to execute a critical 38-minute lunar orbit insertion burn to slide into lunar orbit. Then they'll spend the next 5 weeks reducing their orbit period and getting into formation. During the mission's 3-month science phase, the moon will rotate 3 times beneath the 2 GRAIL spacecraft as they calculate the gravity they encounter. One spacecraft will trail the other in orbit, and each will slow down or speed up in response to the changing gravitational pull from below.
And you need the 2 spacecraft to do that in order to measure the distance between the 2 very precisely.
This data will allow scientists an unprecedented chance to study the gravity of the whole moon, including the far side facing away from Earth, and envision the moon's interior from crust to core. The GRAIL mission also marks the first time students have a dedicated camera on board a planetary spacecraft in order to request photos of specific lunar targets. The Mooncam project is headed by Dr. Sally Ride, the first American woman to fly in space.
What students need to do is to go on mooncam.ucsd.edu, and that's how they register to submit images of the moon. And then the images will be put on the internet for the students to see.
At the mission's end, the GRAIL spacecraft will be decommissioned, eventually impacting the lunar surface. The path from the Earth to the moon has been well traveled in recent decades by pioneers like Surveyor, the Apollo astronauts, Lunar Prospector, and many more. Today, GRAIL is ready to take its place in this long line of lunar explorers.
The moment I'm looking forward to is when we finally get in formation flying and we're really ready to start taking science data for the mission.
I'm going to be passing Complex 17 about 3:30 a.m. on my way to Console. And that hour of the morning, looking off to the east, seeing the rocket bathed in spotlights, it's an emotional time for all of us on the launch team.
This GRAIL mission is set to launch in less than 15 minutes. And let's bring up a live look at the launch vehicle. It holds twin space probes that will orbit the moon in tandem, but they won't arrive there until New Year's Eve. This slow trip is meant to save energy. The probes will study what lies beneath the lunar surface by mapping the moon's gravity. This mission will help scientists understand how Earth and other planets form, but it could also inspire another generation of space explorers. John Zarella joins us now live from Cape Canaveral in Florida. And John, the GRAIL mission, it sounds almost biblical, but explain the acronym and what it's all about.
Yeah, well, it's a gravity mission, as you pointed out, and the bottom line is the weather here is a lot better off than NASA thought it was going to be. And, you know, it struck me that while we've sent people to the moon, we really don't know what's inside the moon. This Delta rocket behind me poised to lift off, as you mentioned, in less than 15 minutes, carrying twin spacecraft that NASA believes will answer that question. The moon. Okay, so we've established it's not really made of green cheese. The Apollo astronauts bagged up more than 800 pounds of rock and dirt.
Soil here is a bit firmer, I think.
What about all that stuff? Isn't that what the moon is made of? Well, that's just what's on top. The fact is, we really don't know what's beneath the surface.
The part of lunar understanding that we don't yet have is what's inside the moon. So to really understand the moon and understand what makes it special, we need to study what's inside.
To do that, NASA is embarking on a unique mission called GRAIL. 2 space probes will fly one behind the other in identical orbits around the moon. The gravitational tug on the probes changes as they fly over various features, mountains, valleys, or masses hidden below the surface. Measuring the change gives scientists, in essence, a lunar CAT scan. That's right, imagine a CAT scan of the moon.
It provides us essentially with picture of the lunar interior, just like you would make a picture of the inside of your body.
It's theorized that the moon was formed from the debris released after a collision between the Earth and another giant body. If that's the case, it will give scientists a better understanding of how the inner planets of the solar system were formed. And in a first, NASA will dedicate instruments, in this case cameras on the probes, exclusively to education. Middle school students and teachers can go to the Mooncam website and request a lunar surface location to be photographed.
And I think once they begin to look at detailed images, when they go out in their backyard and look at the moon, they're going to look at it in a whole new way. And I think that's priceless.
The pictures will be posted in a photo gallery on the internet.
Now, to me, that's probably just as cool as any other part of the mission, Christy. And there's 4 cameras on each of the probes, and middle school students and their teachers, not just in the United States, but around the world, can go to mooncam.com, and it's MOONKAM. So teachers out there, if you're middle school teachers, get on there, start putting in your requests. I think you have to wait till after the first of the year, but get your requests in. That's really cool to be able to take your own photos, have your own photos of the moon taken for your class. That's really neat. Christy?
That's pretty cool. Mooncam.com. And I love how you call this project a lunar CAT scan. John Zarella joining us live. John, enjoy the launch.
Und was da ganz genau passieren soll, das beobachtet jetzt auch mit uns unser Weltraumexperte des Deutschen Zentrums für Luft- und Raumfahrt, Friedhelm Klaasner, ist mit uns telefonisch verbunden. Guten Tag, Herr Klaasner.
Ja, guten Tag nach Köln.
Ja, Herr Klaasner, jetzt erklären Sie doch mal jedem von uns, der nicht gerade Experte ist für Welt- und Raumfahrt, was sollen denn diese Mondsonden letztlich belegen? Warum sind sie so wichtig für die Amerikaner?
Es geht um grundsätzliche Fragen zur Entstehungsgeschichte des Mondes, insbesondere auch um die Frage, was für eine Art von Kern der Mond hat. Bei der Erde wissen wir, dass wir praktisch ein flüssigen Kern haben. Wir haben ein schönes Magnetfeld hier auf der Erde, das schützt uns auch vor Weltraumstrahlung. Beim Mond sieht es etwas anders aus. Entstehungsgeschichtlich ist nach wie vor ungeklärt, ob noch eine flüssige Kernschicht oder ein fester Kern mit einer flüssigen Schicht drumherum am Mond existiert oder nicht. Und das kann man mit diesen extrem genauen Schwerefeldmessungen eben herauskriegen. Man hat festgestellt bei früheren Missionen, dass sich Raumschiffe am Mond ein bisschen komisch verhalten. Obwohl offensichtlich an der Oberfläche sich keine Änderung ergibt, wurden die plötzlich etwas stärker angezogen vom Mond und dadurch auch beschleunigt. Und das ist natürlich eine zunächst mal unangenehme Sache, wenn man überhaupt am Mond ein Raumschiff betreiben will. Das liegt daran, dass Meteoriteneinschläge vielleicht sehr schwere Materialien in den Mond eingetragen haben und dadurch in bestimmten Gebieten eben eine höhere Massenanziehung bedingen. Dadurch, dass man 2 Raumschiffe jetzt am Mond hat, die in einer Höhe von ca. 50 Kilometern und im Abstand von 100 bis 200 Kilometern in den Mond fliegen, merken diese Raumschiffe natürlich diese unterschiedliche Anziehungskraft. Und die Messungen, die man jetzt für den Abstand der beiden Raumschiffe voneinander macht, sind extrem genau. Die sind auf ein Tausendstel Millimeter genau, praktisch so groß wie ein Blutkörperchen. Solche Abstandsänderungen kann man messen. Und das gibt natürlich extrem genaue Aussagen, wie die Schwerkraft genau an der Stelle, wo die beiden gerade drüber fliegen, aussieht. Das lässt wieder Rückschluss zu, wie es innen drin aussieht.
Kurze Frage. Ja? Diese Rakete ist ja unbemannt. Wieso schicken die Amerikaner nicht direkt Astronauten wie damals 69 wieder auf den Mond, die das alles überprüfen? Was ist denn jetzt das Gefährliche daran, dass keine Menschen momentan auf diesen Mond können?
Zunächst mal ist das eine Aufgabe, für die man keine Astronauten braucht. Das wäre also völlig überzogen, wenn man hier Menschen irgendeiner Gefahr einer Raumfahrtmission aussetzen würde. Das können diese beiden kleinen Satelliten, ich meine, die haben eine Größe von jeweils knapp einem Kubikmeter. Das können die viel besser machen. Der Mensch würde da oben nur stören. Sobald sich ein Mensch irgendwo bewegt, wäre diese Abstandsmessung gestört. Da gibt es zum Beispiel eine Besonderheit bei der Mission. Man fliegt da insgesamt 3,5 Monate zum Mond. Man schießt also nicht direkt Richtung Mond, sondern man fliegt relativ langsam zum Mond hin. Man will diese lange Zeit haben, um ein Ausgasen, also irgendwelche Restgase, die in den Oberflächen von den Raumschiffen drin stecken, rauszukriegen. Denn allein das Ablösen von solchen geringen Gasmengen, die noch irgendwo vorhanden sind, würde schon die Abstandsmessungen wiederum stören. Der Mensch hat bei dieser Mission überhaupt nichts zu suchen. Er würde ganz furchtbar stören.
Aber 3,5 Monate klingt nach einer sehr langen Zeit. Wann kann denn dann überhaupt mit ersten Ergebnissen für uns Menschen gerechnet werden?
Die beiden Raumschiffe werden am 31. Dezember und 1. Januar kurz hintereinander am Mond ankommen. Dann wird es am Mond noch eine ganze Zeit lang dauern, bis die wirklich auf einer schönen kreisförmigen Bahn um den Mond laufen. Und zwar auf einer polaren Umlaufbahn um den Mond. Und man muss auch den Abstand der beiden Raumschiffe vorher sehr genau einstellen. Also Höhe und Abstand muss stimmen. 50 Kilometer hoch über der Mondoberfläche ist sehr nah dran. Und der Abstand 100 bis 200 Kilometern wird je nach Messziel definiert. Man kann das irgendwie vergleichen vielleicht mit einer Ultraschalluntersuchung, der wir uns aussetzen. Da werden jetzt praktisch von außen Schallwellen in den Körper eingebracht und geguckt, wie es reflektiert wird. Hier wird geguckt, wie sich die beiden Raumschiffe unterschiedlich anziehen lassen von der Mondoberfläche. Je näher die beieinander sind, umso höher ist die Auflösung. Umso genauer kann man sagen, wo ist jetzt eine Massekonzentration auf dem Mond oder wo ist die Masse sehr gleichmäßig verteilt. Und das ist vor allen Dingen ein Phänomen, das ist der erste Formationsflug von zwei Raumschiffen, der nicht an der Erde, sondern außerhalb der Erde an einem anderen Planeten, an einem anderen Himmelskörper stattfindet. Hier auf der Erde haben wir die sogenannte Tandem-X-Mission für die Erdbeobachtung, wo zwei Satelliten im geringen Abstand mit Radarstrahlen die Erdoberfläche abtasten und Höhenprofile erzeugen. Es ist sowas Ähnliches wiederum. Das hat man noch nie an einem anderen Himmelskörper gemacht. Und das ist natürlich eine besondere Kunst, auf der Entfernung von knapp 400.000 Kilometern zwei Raumschiffe dann in so einem geringen Abstand exakt zu manövrieren.
Herr Klaassen, wir sehen parallel, während Sie sprechen, Live-Bilder aus Cape Canaveral. Dort sehen wir eine rauchende Rakete und eigentlich ist es jetzt 14:37 Uhr und diese unbemannte Rakete sollte jetzt abheben. Sagen Sie uns doch ein bisschen was zu den A, Zeitplänen und B, was erwartet uns denn da jetzt hoffentlich in Sekunden oder Minuten?
Also in Sekunden oder Minuten wird uns nichts erwarten. Zunächst der Reihe nach. Der Rauch, den wir sehen, das sind abgasende Treibstoffe, die praktisch kryogen sind und einfach kalt sind und dadurch die Feuchtigkeit in der Luft kondensieren lassen. Das sind einfache Wasserwolken ganz normal dabei. Dann haben wir im Moment die Situation, dass in oberen Luftschichten starke Querwinde sind, die außerhalb der akzeptablen Limits für den Start liegen. Im Moment ist der Countdown weiter angehalten. Die nächste Startchance ist, wie NASA eben mitteilt, um 15:16 Uhr heute Mittag.
Das ist deutsche Zeit oder amerikanische Zeit?
Das ist mitteleuropäische Sommerzeit, also unsere Zeit. Das habe ich gerade schon umgerechnet. Das wäre also ungefähr in einer guten halben Stunde. Mhm. Und das Launch-Team macht jetzt weiterhin Systemchecks, prüft, ob alles in Ordnung war. Es war also bis zu einem Zeitpunkt 2 Minuten vor dem Start alles im sogenannten grünen Bereich, keinerlei technischen Probleme. Nur das Wetter hat nicht mitgespielt. Das kommt vor, das war von vornherein nur eine 40-prozentige Chance, dass zu diesem Zeitpunkt das Wetter gut ist. Ungefähr 10 Minuten vor dem Start war auch alles im grünen Bereich, inklusive Wetter. Das hat sich leider gedreht, damit muss man leben. Also eine halbe Stunde Geduld ist noch angesagt. Ich weiß nicht, wie Sie das in Ihren Sendeplan jetzt einbringen können. Ist natürlich eine spannende Sache.
Und Zuschauern natürlich so zeitnah wie möglich dann auch diesen Start zeigen, auf den wir uns ja jetzt so vorbereiten. Können Sie uns noch kurz beschreiben, ob es dann ähnelt einem Shuttle-Start, dieser Start der unbemannten Rakete?
Nein, das ist eine unbemannte Rakete, die etwas höhere Startlasten aufbringen kann, was die Beschleunigung betrifft. Die wird also nicht ganz so langsam majestätisch abheben wie ein Shuttle, sondern wird relativ schnell wegzischen, wenn man das mal so lapidar formuliert. Die haben einfach höhere Beschleunigungen, die dabei möglich sind, denen man einen Menschen nicht aussetzen würde. Ansonsten, was die Startbilder betrifft, den Feuerschein, die Raucherscheinungen, das wird alles sehr ähnlich sein.
Dank für den Moment. Wir werden natürlich live berichten, 15 oder 16 Uhr, je nachdem, wann diese unbemannte Rakete dann hochgehen wird Richtung Mond. Und wir machen im Moment erstmal weiter mit einem NTV News Spezial.
The first launch window has come and gone, but as you can see, live pictures here, the spacecraft is still there, it's still on the ground. Now, NASA has waved off the first attempt because of strong winds, but they will try again in about 20 minutes. And that is Newsstream. But the news continues at CNN. World Business Today is next.
LC, this is LD on Channel 1.
Go ahead.
Yes, sir. The upper level winds are still red at this time. There isn't sufficient time to get another balloon, and so we need to set up for a 24-hour recycle.
Roger that. RC copies.
This is Delta Launch Control, and as we heard, we will scrub for today due to upper level winds. Our initial time on Friday will be 8:33 a.m., 8:33:25 to be precise. And our second opportunity on Friday is 9:12 or 9:12:31 to be exact. This is Delta Launch Control. We're backing out of our countdown, getting ready to detank the liquid oxygen. And there was a decision that we will also detank the RP1 fuel. So both those commodities will come off, and then the mobile service tower will go back into position around the rocket. Our plan for NASA TV coverage tomorrow is that we will begin at 5:45 a.m. Eastern Time, which will be concurrent with the reloading of the RP-1 on board and all of the other pre-launch activities that will follow. This will conclude our coverage for the Delta II GRAIL launch. This is Delta Launch Control. This is Delta Launch Control at T-minus 134 minutes, 37 seconds, and counting. The countdown picked up on schedule this morning for the launch of the Delta II rocket with GRAIL. Right now in the countdown, the helium tanks aboard the first stage are being pressurized in preparation for loading the RP-1 fuel on board the first stage, which is scheduled to begin in about 5 minutes. The RP-1 is a highly refined kerosene fuel, and that will be followed by loading the liquid oxygen on board. Right ahead of that, we will have a weather briefing for this morning. And at this time, everything is proceeding on schedule for a liftoff at 8:29 a.m. To be precise, will be just 45 seconds past the 8:29 mark at 8:29:45 for ignition of the main engine on the Delta rocket. The GRAIL spacecraft reports that they are go for this morning's launch, and right now in the countdown, the spacecraft test team is on station. We do have a second opportunity this morning, once again, at 9:08, should that be necessary. At this time, we are planning for 8:29, and no indication at this point in time that we will be needing to target that second opportunity at 9:08. Weather appears to be generally favorable. And right now, the balloons are being released to assess the upper level winds. And in about another hour, we'll have our launch director, Tim Dunn, come over and give us a status. So now we will join the launch team and hear the preparations for loading the RP-1 fuel aboard the Delta first stage. At T-minus 132 minutes, 12 seconds and counting, this is Delta Launch Control.
All stations on NLM net, this is the NLM with the final readiness for launch poll. Give a brief status. We have configured the vehicle for the second opportunity today, the 99-degree azimuth. We have loaded mission constants with the daily reset and the load relief file. Currently the range is green, SCO box is clear, TDRS is configured for the 99-degree azimuth. Weather is green, and most importantly, our upper level winds are green. So with that, I'll begin the poll. Please respond go, no go. NASA CE.
NASA CE, go.
NASA MEM.
NASA MEM, go.
SMA.
SMA's go.
SMD.
GRAIL is go for launch.
NAM.
NASA advisory team is ready.
Copy that. The NASA team is ready for launch.
Count minus 9 minutes. Following personnel, report ready to proceed with countdown and remain on channel 1. Report go, no go. ECS?
Go.
ATC-2?
Go.
ATC-3?
Go.
EEA?
Go.
ESYS?
Go.
FMA?
Go.
SYS?
Go.
TM1?
Go.
TM2?
Go.
MEA?
Go.
PEA?
Go.
Prop 1?
Go.
Prop 2?
Go.
SSC?
Go.
SSP?
Go. Go.
FSC?
Go.
GE?
Go.
HYE?
Go.
VE?
Go.
VP?
Go.
VSE?
Go.
SCM?
Go.
OSM?
Go.
RC, range, weather, and final clear to launch. Go. NSC?
Go.
AC?
AC is go.
Post-launch securing will be conducted on Channel 15. Flight data will be reported real-time on Channel 2. Following personnel switch to Channel 15 after liftoff is confirmed for pad securing. LC, Prop 1, ATC 2, Prop 2, SSP, OSM, SSC, Talker, FSC, and ATC 3. Personnel, if a condition that exceeds the launch constraint is observed during the final 4 minutes, the observer shall call a hold on the countdown. Launch Ops Net Channel 1, as directed by the console operator's memo. There are no expected or allowable alarms after T-minus 60 seconds. All personnel remain on Channel 1 until after launch. In the event of a hold after T-minus 4 minutes, recycle steps will begin in Appendix K. Appendix K is the yellow pages. To prevent the possibility of a hang fire, personnel with launch enable switches are instructed not to switch launch enable to off or open after T-minus 4 seconds. In case of engine cutoff or no vehicle liftoff by T+5 seconds, recycle and safing will be performed for Appendix L. Appendix L is the red pages.
This is Delta Launch Control, T-minus 4 minutes and holding. We will be coming out of the hold at T-minus 4 to begin our final countdown for a mission that will study the moon from the surface to the center of the moon.
Minus 6 minutes.
LC, this is the LD on Channel 1. You have permission to launch.
Roger, proceeding with the count.
Okay, that confirmation from our United Launch Alliance Launch Director, Kathy McLaughlin, that we will be picking up the count. Spacecraft GRAIL has been told to begin their preparations to go to internal power.
minus 5 minutes.
LC, verify water pressure is 125 plus or minus 25 psig.
Verify.
Establish countdown limit conditions, T minus 4 minute on.
On. Load relief is verified.
All personnel stand by for release of the hold.
And the GRAIL spacecraft confirms they're now on internal power, standing by for releasing the hold in 30 seconds. Coming out of the hold in 5, 4, 3, 2, 1. T minus 4 minutes and counting.
SSC, perform vehicle internal transfer.
Active. TM internal. Control internal.
Complete.
SSC, perform vehicle arm.
Active. Forward arm.
Script complete.
OSM, solid motor, SNA arm permit closed.
Closed.
FSC, all solid motor ignition and separation to arm.
Arm.
T minus 3 minutes.
Prop 1, vehicle fuel tank press open.
Open.
Fuel umbilical purge open.
Open.
FSC, BAT 1 heater control exit.
Exit.
BAT 2 heater control exit.
Exit.
NSC, report spacecraft go. GRAIL is go.
T minus 2 minutes, 2 minutes to launch.
FTS BAT 1 and 2 heaters off.
Off.
Prop 1, pressurized first stage LOX tank to release.
Pressurizing.
110 seconds.
Prop 2, top first stage LOX to 100% level.
Topping to 100%.
Seconds.
SSC, hydraulic external power on.
External. Seconds.
RCO, report range go for launch.
Range go for launch. 70 seconds.
SSC, hydraulics internal.
Internal.
T minus 1 minute and counting.
LC, countdown limit conditions, T minus 60 seconds on.
On.
Seconds.
LC 17B, launch enable to flight.
Flight.
ATC 3, main power disable, on.
On.
100%.
35 seconds.
Hydraulics go.
30 seconds.
Got it.
22 seconds. 20 seconds. 15 seconds. 13 seconds. 11.
Green
T
board.
minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 0 and liftoff of the Delta II with GRAIL on a journey to the center of the moon.
Chamber pressure rising in all 6 grounded solid motors. Good chamber pressure on the main engine. Good chamber pressure on both verniers. Good chamber pressure on all 6 groundlet motors. 20 seconds into the flight. We have 29 seconds. Mark, 29 seconds, Mach 1, vehicle now going transonic. 35 seconds in. 38 seconds in, max Q, maximum dynamic pressure in the vehicle. Coming up on the 45-second mark. Mark, 45 seconds in, altitude 3.4 nautical miles, downrange distance 13.4 nautical miles, velocity 1,742 miles per hour. Coming up on the 1 minute mark. Mark, 1 minute into the flight, standing by for solid motor burnout, about 10 seconds from now. Pressure decreasing in the solids. Standing by for burnout. And we have burnout, standing by for SEP. And we have separation. And we have ignition on the 3 airlet motors. The 3 airlet motors have come up on chamber pressure. Chamber pressure on the airlet motors. 1 minute 39 seconds into the flight. The Delta vehicle now only weighs about 1/2 of what it did at launch, expelling propellant now at the rate of about 2,700 pounds per second. 1 minute 50 seconds in. Altitude now 21.8 nautical miles. Downrange distance 51 nautical miles. Velocity 4,493 miles per hour. About 30 seconds now remaining on our 3 airlet motors. Chamber pressure is beginning to decline. We have a good engine control in the main engine, good engine control in the verniers, settling down from the initial launch transients. Standing by for burnout of the 3 airlet motors. And we have burnout, standing by for separation. And we have separation. Separation on the airlet motors. Now 2 minutes 50 seconds into the flight. Altitude now 41.7 nautical miles. Downrange distance 130.7 nautical miles. Velocity 7,761 miles per hour. 3 minutes into the flight. Smoother ride now. Main engine pitch and yaw control is good. Well within our ability to control. Vernier engine pitch and yaw control is good. 3 minutes 15 seconds. Chamber pressure holding very well in the first stage. Main engine chamber pressure right where we want it to be. Vernier engine control and chamber pressure is right where we want them to be. Coming up 3 minutes 30 seconds. Mark, 3 minutes 30 seconds, now at Mach 15. Less than 1 minute until main engine cutoff. Vehicle now at 59.7 nautical miles, downrange distance 240.3 nautical miles, velocity 10,000, correction, now 11,281 miles per hour. Coming up on the 4 minute mark. Mark, 4 minutes into the flight, less than 20 seconds now until main engine cutoff. Four minutes 15 seconds in, standing by for main engine cutoff about 5 seconds from now. And we have MECO, standing by for vernier cutoff. And we have vernier cutoff, stand by for 1-2 SEP. And we have 1-2 SEP. And ignition on the second stage. Good ignition on the second stage. And we have fairing separation. Good fairing separation. 4 minutes, 50 seconds in. 4 minutes, 55 seconds. All looks good. Good engine control in the second stage. As we pass 5 minutes, 5 seconds, altitude now 80 nautical miles, downrange distance 504 nautical miles, velocity 15,135 miles per hour. 5 minutes, 15 seconds in. This first burn of the second stage today will last about 2.5 minutes. Coming up 5 minutes, 28 seconds in. Altitude now 84 nautical miles, downrange distance 588 nautical miles, velocity 15,440 miles per hour. 5 minutes, 40 seconds in. Second stage chamber pressure continues to hold right where we want it to be as we're coming up on the 6-minute mark. Mark, 6 minutes. Looking good. And receiver decoders are confirmed off at this time as we're approaching 6 minutes, 20 seconds. Mark, 6 minutes, 20 seconds in. Altitude now 90 nautical miles, downrange distance 776 nautical miles, velocity 16,141 miles per hour. Just got confirmation from AE that we are now on Tidris, 46 degrees. Data. 6 minutes, 45 seconds in. Standing by for SECO 1. About 20 seconds from now. Pressure beginning to decline. And we have SECO. Hydraulic system pressure now declining. Pumps off. 7 minutes, 35 seconds in, altitude 92.6 nautical miles, downrange distance 1,069 nautical miles, velocity 16,903 miles per hour. Delta flight commentary at 8 minutes, 15 seconds in. The second burn of the second stage will occur about 57 minutes from now. We'll be on broadcast intermittently between this time and that, bringing you up updates as the flight progresses. And the next scheduled burn, the second burn of the second stage, about 1 hour, 5 minutes, and 49 seconds into the flight.
And we're now in a parking orbit. This is a coast phase, as we heard, that will last about 57 minutes. All of the data coming in here to NASA Hangar AE, our telemetry facility, is indicating we've had a very good flight of the first stage and the initial burn of the second stage. Solid rocket boosters all burned well and jettisoned on schedule and on target.
To what we expected. 9 minutes, 51 seconds in. Altitude now is at 93.9 nautical miles. Downrange distance 1,611 nautical miles. Velocity 16,901 miles per hour.
This is the Mission Director Center, where right now we have a team that is now suddenly very relaxed, and we'll be able to stay that way for another 55 minutes or so. Right now the GRAIL spacecraft appears to be in a good state of health as it coasts along atop the second stage in a parking orbit. Data we got back so far indicates that the parking orbit is almost exactly nominal and where we want it to be. And the performance data from both stages looks good.
12 minutes, 20 seconds into the flight. At this time, we are in the process of our barbecue or roll mode, rolling at about 1 degree per second. We'll continue in this mode for about another 20 minutes. 10 seconds now till deploy. Standing by. We have GRAIL A brake wire and separation. Good separation. GRAIL A now flying on its own. We have brake wire and separation. Good separation on GRAIL B. Ready to begin the journey to the moon. Hour, 28 minutes, 27 seconds into the flight.
And joining us here at the console in the Mission Director Center is Tim Dunn. He was the NASA launch director for this flight, and Tim, congratulations, because the NASA administrator has just given you an award and some congratulations. And
well, thank you, George.
Tell us briefly what did he say to you?
Well, it was just a special opportunity for us as a launch team to have the administrator with us. He sat with us on console and recognized the team after we had successful GRAIL A and GRAIL B separation. So it's a special moment that the team's enjoying right now with the NASA administrator.
Well, the countdown was interesting. I guess added a little bit of suspense and drama, because it looked like we were almost face to face with exactly the situation we had on Thursday with the upper level winds. But how did they work through that? It sounded like they were busy in Denver working software to try to help us get a program that would get us to launch.
Exactly. We had a great countdown today, very smooth countdown for the launch vehicle. We had no launch vehicle anomalies. The Delta II rocket just absolutely is a gem in getting it ready to launch. The range, we had a beautiful range today. All downrange assets were operational. Our spacecraft was ready to go, had no SV issues. So the only issue we were working throughout the count was upper level winds again. And we briefly went green about midway through the count, right as we were doing LOX loading. Then put another balloon up and got red data again. And as you mentioned, we worked our way through that.
Right now we've got one more launch replay we want to show you, which was taken from Port Canaveral down at Jetty Park of the launch earlier this morning at 9:08. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and liftoff of the Delta II with GRAIL on a journey to the center of the moon.
Chamber pressure rising in all 6 grounded solid motors. Good chamber pressure on the main engine. Good chamber pressure on both verniers. Good chamber pressure on all 6 groundlet motors. 20 seconds into the flight. We have 29 seconds. Mark, 29 seconds. Mach 1. Vehicle now going transonic. 35 seconds in. 38 seconds in. Max Q. Maximum dynamic pressure in the vehicle. Coming up on the 45-second mark. Mark, 45 seconds in. Altitude 3.4 nautical miles. Downrange distance 13.4 nautical miles. Velocity 1,742 miles per hour. Up on the 1 minute mark. Mark, 1 minute into the flight. Standing by for solid motor burnout about 10 seconds from now. Pressure decreasing in the solids. Standing by for burnout. And we have burnout, standing by for SEP. And we have separation. And we have ignition on the 3 airlet motors. The 3 airlet motors have come up on chamber pressure. Chamber pressure on the airlet motors. 1 minute 39 seconds into the flight. The Delta vehicle now only weighs about 1/2 of what it did at launch, expelling propellant now at the rate of about 2,700 pounds per second. 1 minute, 50 seconds in. Altitude now 21.8 nautical miles. Downrange distance 51 nautical miles. Velocity 4,493 miles per hour. About 30 seconds now remaining on our 3 airlet motors. Chamber pressure is beginning to decline. We have a good engine control in the main engine. Good engine control in the verniers, settling down from the initial launch transients. Standing by for burnout of the 3 airlet motors. And we have burnout, standing by for separation. And we have separation.
Nach tagelangen Verzögerungen sind die beiden US-Raumsonden GRAIL A und B zu ihrer 9-monatigen Erkundungsreise um den Mond gestartet. Die Sonden sind etwa so groß wie eine Waschmaschine und sollen das Schwerefeld des Mondes vermessen. Und daraus können Forscher dann Rückschlüsse auf die Strukturen im Mondesinneren ziehen.
1, 0 and liftoff.
Endlich weg. Zweimal passte das Wetter nicht für den Start der Delta-Trägerrakete und selbst im dritten Anlauf konnte sie erst mit einer halben Stunde Verspätung vom Weltraumbahnhof in Cape Canaveral abheben. An Bord sind 2 US-Raumsonden mit dem Namen GRAIL, jede so groß wie eine Waschmaschine. Mehrere Monate lang sollen sie das Innere des Mondes erkunden und dabei Daten liefern, aus denen die Wissenschaft herausfinden kann, wie Erde, Mond und andere Planeten entstanden sind. Die NASA kann dringend einen kleinen Durchbruch brauchen. Das Atlantis-Shuttle-Programm ist beendet. Was bleibt da noch, außer vielleicht den Aufnahmen von Wirbelstürmen, über die sich jeder Meteorologe freut. Und so wendet sich die NASA wieder dem Mond zu. Nur wenige Tage vor dem Start heute präsentierte die nationale Luft- und Raumfahrtbehörde in einer Hollywood-würdigen PR-Aktion Bilder aus einer guten alten Zeit. Ende der 60er fühlten sich die Amerikaner als unangefochtene Herrscher im Weltraum, obwohl sie auch damals nicht allein im All waren, aber der erste Mann auf dem Mond, das war ein Amerikaner. Solche scharfen Bilder von der Mondoberfläche hat es bis jetzt noch nie gegeben. Nicht nur die Landeplätze der einzelnen Apollo-Missionen sind zu erkennen, selbst die Fahrspuren der Mondbuggies sind auf den Aufnahmen deutlich zu sehen. Da sage noch einer, die NASA habe die Mondlandung nur vorgetäuscht.